Okay, so to wrap up the discussions of Java Semaphore, we're going to talk about some of the usage considerations to keep in mind when you program with semaphores. And this discussion is broader than your particular assignment, but it's got some stuff you'll also be able to use in the assignment as well. So semaphores are a lot more flexible than the more simple Java synchronizers. So things like synchronized statements, things like reentrant lock, those are some of the sort of simple mechanisms, and semaphore is more flexible. Needless to say, that's actually not how flexible I am, but it could look that way. In particular, you can atomically acquire and release multiple permits with a single operation, which is something you really can't do with the other mechanisms. You can't acquire the lock 5 times with a reentrant lock or with a synchronized statement. But with a semaphore, you can acquire multiple things with one atomic operation. The acquire and release methods need not be fully bracketed. For synchronized statements, for Java reentrant locks, they are required to be fully bracketed. The thread that acquires it must be the one to release it. But with semaphores, as we saw with the ping pong example, they could go back and forth. Naturally, these extra features come at some extra cost. So semaphores are not really as lightweight as reentrant locks. But that's okay, because well, the thing to remember is always try to use the lightest weight mechanism that fulfills your requirements. If you need more than what you get from the simple things, you're probably going to have to pay a little more in terms of the features. If you want the stuff that's simple, or you can live with the stuff that's simple, you'll get faster performance as a consequence. When a semaphore is used for a resource pool, like the Palantiri that we've been talking about, all it does is it simply tracks the number of free resources. We know that we've got 2 resources available. However, it doesn't track which resource or resources are free. It just knows that there are 2 of them. It doesn't know which 2. It just knows there are 2 of them. So if you want to be able to figure out which ones you're going to need, then you have to use some other mechanism to keep track of the particular ones. So do you want to use a list? Do you want to use a hash map? Do you want to use a set? Do you want to use a tree map, or whatever? And that actually becomes very significant when you start programming assignment 1B. Hopefully you're already there, because you've got to use 2 different things. You've got to be able to figure out if there's something available, and a semaphore is great for that. But then once you know something's available, you got to find the right thing. And finding the right thing is also a concurrency issue, and so you'll have to use the proper synchronizers to guard access to whatever data structure is keeping track of what the available things are, as opposed to, is there an available thing? That's what the semaphore is used for. The semaphore is there something available? And then we have other data structures, like a hash map in your case, that have to be protected by other synchronizers, like a spin lock, or a synchronized statement, or a reentrant lock, or something else. So you'll get more experience programming with those things as well. As I just said, these mechanisms require synchronizers, either ones that you add or ones that are built in. For example, when we come later and we use a concurrent hash map, they have synchronization built in. So you have to worry about a different set of things. Semaphores are fairly straightforward. They're not too hard to understand, because they don't really do a heck of a lot, right? They increment and decrement counts. But they can also be a bit tedious and error-prone to program, because they have some limitations. One limitation that you can run into if you're not careful is you can end up holding a semaphore for too long a period of time without really needing it. So you can lock other threads out unnecessarily. So here's a simple example where we have some method. We've got a semaphore. Let's say it's a binary semaphore. It doesn't really matter. We acquire the semaphore. Then we do some things that does not involve that semaphore, but we've got it locked. We've got it acquired. And then we do something that doesn't really need it to be locked, and we're blocking anybody else out from getting access to it while this thing is running in some big loop. And then finally we'll release it. So this means that other threads won't be able to acquire the semaphore because we got it locked out for a long time. So if you've got a situation like that, you might sort of think to yourself, do I really need to keep that semaphore locked the whole time I'm in this long-running computation? Maybe not. Another problem is releasing the semaphore more times than you actually need to. So here's a case where we come along, we acquire the semaphore, so far so good. We do a bunch of stuff, so far so good, and then we call release multiple times. We call 3 releases for this one acquire. And what that'll do is that'll increment the count perhaps incorrectly, so that other threads will now think, oh wow, we got lots more resources available. We actually don't have more resources available. You just accidentally incremented it multiple times. Now you might ask yourself, how the heck would you ever do this, right? Who would ever do something so stupid as to call release 3 times? Well, you probably wouldn't call release 3 times, but you could have some code you could have a complex flow of control in a method where there were multiple points of exit from blocks or the method, and you might mistakenly release it on multiple paths. And that's a very easy thing to do. So be careful with this. This is a really annoying bug. Another equally annoying bug is to acquire a so if releasing the semaphore too many times is a problem, another problem is acquiring the semaphore and then forgetting to release it. This is probably even more common problem. So here we come along, we acquire the semaphore, we've got some critical section, and then we return from the method without actually releasing the semaphore. Now, sometimes that's perfectly fine. If you don't have fully bracketed semaphore usage, that may not be a bug. But if you expect to have fully bracketed semaphore usage and you return without releasing the semaphore, then that semaphore will be locked indefinitely, and that can cause all kinds of problems. The point you should hopefully be coming away with from this is that semaphore usage is a bit brittle. A good idea, because of what I just talked about, because it's easy to forget to release things, you should get in the habit of always using semaphores with try finally blocks. So here's an example. We acquire the semaphore, we then do some stuff, we return from this, and in the finally part, we release the semaphore. So if you get in the habit of doing that, and you need fully bracketed semaphore usage, then this will save you. This advice also applies for other synchronizers as well, things like reentrant locks, as you'll see later. Now, the synchronized statements and methods that are built into the Java language handle this for you automatically, because the way that a synchronized method or a synchronized statement works is that it follows the syntactic block-oriented structure of the Java language. And so if you have, say, a synchronized method, it'll automatically acquire the synchronizer on entrance to the method, and it will automatically release it on exit from the method. So then you don't have to worry about this. But if you're using the objects and classes that are provided as part of the Java class library, Java util concurrent, locks, reentrant lock, semaphore, whatnot, then you should get in the habit of using the try finally blocks. Semaphores are rather limited synchronizers that don't really scale up to complex coordination use cases. So when you need more complex coordination than just, what's the count? Is it greater than 0 or not? Do something. You probably want to use other mechanisms. And in particular, condition objects, which we'll talk about later, of course, are a better choice for most complex coordination use cases. And that's because condition objects let you wait for arbitrarily complex conditions, hence the name condition object, that you can control. You write those conditions, conditional expressions in loops typically. And as a result, they're much more powerful, whereas a semaphore is like increment, decrement. That's about all you can do with it. So we'll talk about those things a bit later. Okay, so that's the end of the Java semaphore discussion.